Hi, welcome to the video. So basically what I'm going to do is I'm going to talk through the COVID-19 tracker that I built for my cloud systems assignment for DCU. First, I'm going to show you the application, and then we're going to go through this little slideshow that talks through how it was built. So this is the dashboard that was built for this assignment. So the way that this works is we track all the different cases of COVID-19 coronavirus that have happened over time, and we've plotted the geo-coordinates onto the map. And the data that we track is the confirmed cases, the recovered cases, how many people have died, and then we calculate how many active cases there are currently. So this data is synced daily from a data source, which we'll discuss later. And we update some databases and some caches, and then we render the results periodically. We've also added some very broad metrics at the top. So we've got the total aggregate cases for both confirmed, deaths, recovered, and we show how many countries have been affected by this. We've also got some news, so we've got live news updates as they happen, which come into the application, and then we've also got a breakdown of what percentage of what country. So these are the top 5 countries at the moment that are being affected, or top 4, I believe. And then we've also got some basic charts that show, change over time and different things like this. We've got a full list of all of the data for the current date, which you can break down and filter. So for instance, Ireland, yesterday there were 5,464 cases, 170 people have died, 25 have recovered, and there is currently, well, as of yesterday, 5,165 active cases. So this is kind of the aggregated, consolidated data that we've gathered from our data source, and we've done some processing on it to produce this table. We've also got some live news updates, which come in via the News API, which is a free API that you can request news articles for. So we use a couple of keywords, COVID-19, coronavirus, and some others. And basically, as news happens, we sync it and push it to this web user interface. The whole application is using real-time technology, so there's no request. You can leave this application open in your browser and it will update with new news articles over time. As you can see, we've been running this for quite some time, and there's a good history, a chronological order of coronavirus with regards to the news. As you can see here, 27th of March, Boris Johnson test positive. A few weeks before this, he was saying it was not a big issue. So you can look through this news. It's quite interesting to see the evolution of news over time. We've been tracking the news for quite some time. I think going back to even the start of March, there's quite a lot of news there. So that's basically the application in a whole. And now let's talk about how we built this. So I'm going to present this. So the COVID-19 tracker, how it works. So we're going to go through 4 topics. So first of all, the motivation behind the application that we built, the data sources that we used, the technology that makes it work, and then how it actually works under the hood. So let's get stuck in. So what was the motivation for this? So as I showed before, you can see that over time, the coronavirus has spread, originating in Wuhan in November/December of 2019. And then the first kind of documented cases were early January of 2020. So over time, you can see that cases have started to spread across the world. And when we first started looking at coronavirus back in mid-January, there was really only a few cases in China, and China was the big hot zone. And over time, as we've been processing this data, we've gradually seen, the case rate change over time, and we've seen the whole globe has basically been affected by this. Some hotspots, as you can see in New York and America as a whole, and a lot of Europe, Italy, Spain, France, Germany are getting hit hard. So the goal of this was really to try and see the spread over time. And at the time when we first started looking at this in January, there was very few dashboards, if any. I think John Hopkins was the only one, and then there was a couple that came up pretty quick after that. So taking a kind of an interest in the data, it was perfectly in time for this assignment where we had to do some data processing using cloud technologies. So at the time, we weren't really thinking about the massive amount of cases that we see globally, but it was very interesting kind of project at the time to analyze some data from China and watch it over time and see how it evolved. So it was a good opportunity to build an application that could pull the data from our data source, periodically do some analysis on it, and then produce some charts and graphs. So that was kind of the motivation for this application. So charts and graphs and maps are nothing without data. So where do we get the data? So Johns Hopkins University was one of the first organizations to consolidate the data and make it publicly available. So what they did was they started publishing the case data that they had gathered from various sources, and they started publishing it to a public GitHub repository on a daily basis. So within their repository, they've quite a number of CSV records. So each day there's a CSV record, and they go all the way from today back to mid-January, which is when we first started taking an interest in this. As you can see, they've been uploading this in an automated way. And one of the interesting things is that, which is perfect for a data processing assignment, is the change. The data at the start had a certain format. And over time, as things got a lot more serious with coronavirus, this data started to evolve into various different things with a lot more detail, a lot more quality, various fields have been added, longitude and latitude. And we can follow this trend over time. As you can see, the latest records have even more data in there. So when we first started looking at this, the data was very rough and ready. And now we've got this very concise data set with various different features. Which is interesting because when we first started working on this project, we were trying to build a data set that looked very like this. And obviously we had to deal with data not existing, and then eventually it existed. So, it was a very interesting project to work on with regards to that. So as we spoke about, as we've seen from the repository, the data is updated daily by Johns Hopkins. And at the time when we first started working on this project, there was very little rate of change between each day. And this wasn't a global pandemic. So the data was, fairly static, and it would grow slightly over the days, and then we would just sync that data. So what we did was we wrote some application logic that would basically sync code or sync the CSV files from that GitHub repository on a daily basis, and then trigger our data processing. And what we decided to do was we decided to use Apache Pig and Apache PySpark for two reasons. One, as we spoke about earlier, the data was in a strange kind of format. Fields were null, dates were different over time, things were changing between each day of records as the data improved. So we used Apache Pig to kind of sanitize the data somewhat. So, we replaced empty fields with, 0 values for integers. We swapped out null values, places where there was no partial addresses, we kind of fixed them up a little bit. We also removed addresses that weren't real. So for instance, there was the Diamond Princess. A lot of the records related to the Diamond Princess cruise ship were in a kind of a strange format. So we had to deal with a lot of that. And then we did some extra aggregation. So we wanted to figure out how many active cases there are. We didn't want to have to constantly calculate active cases anytime we rendered that data. So we used Apache PySpark to basically, sum up fields and add a new column into a data set. We also wanted to know what the unique countries were. As this started to spread from more countries than China, we wanted to know, what were their unique countries and what were the sum of cases for those countries. A lot of countries have very good data. Some countries only have the country totals for the day. So for instance, the US, as we see in this map, has substantial cases, and there's very high granularity on the data. You can see all the different locales, whereas for instance, Spain, you get a daily rate. Brazil, you get a daily rate. China, you get a daily rate. So we wanted to really kind of work with those the granularity. So PySpark allowed us to aggregate all of these numbers into consolidated fields. So we were able to produce new data sets from our out of our original data set and kind of, you know, optimize the presentation of some of this data. So what kind of tech did we use to do all of this? So being an assignment to build technology for the cloud, we used a bunch of different cloud native technologies. First of all, we wanted to have our infrastructure in the cloud predictable. So we decided to use Terraform. And with Terraform, it's a fantastic product from HashiCorp. You can essentially automate cloud infrastructure across a number of different clouds, and you can run it in a predictable way. So if you needed to spin up a new environment, you can run your Terraform code, and it will essentially create all of those resources in the cloud as described by your Terraform files. So we have a Git repository with all of our Terraform code in it. As you can see, we do things like create storage buckets, we create a Dataproc server, we create user accounts, we do loads of different things. So there's some interesting stuff in here. One of the interesting things we did with this was we didn't want to have to manually run this all the time. We wanted it to be very, very automated. So one of the things we did was we wrote a GitLab continuous integration file that could run our Terraform using some service account credentials that we saved into some secret variables. And basically, every time we made updates to this repository, the CI would trigger, and we could basically run our Terraform against the cloud, which meant we didn't have to have, you know, do a lot of stuff on our command line. We could basically automate this. And even if we didn't want to run changes, we put some manual triggers on the actual Terraform apply target. So it might be that we wanted to make a bunch of changes, but we didn't actually want to run the Terraform until we were ready. So we put these triggers on it that GitLab then would pause the execution of that Terraform until we manually decided to click a button in our CI, which was a very useful way for building this project because it meant we could iterate the code without actually having to tear down an environment. So what else do we use? So as you can see, there's a bunch of different components already, you know, just starting to come out. There's the dashboard itself, there's the syncing of the data, and then there's a load of back-end logic in the middle that we haven't discussed yet. So this kind of lent itself to a microservices architecture where we built a load of loosely coupled services and we kind of combine them together using various different technologies. So one of the main things about building microservices is that as long as the interface between the services is clearly defined, it's very easy to swap services, rewrite them completely, distribute them in a different manner. And as long as they can talk to each other using a predefined interface, it's very easy to iterate services quickly. So that was a model that we were quite familiar with using. So that was a model that we took here, and it allowed us to rapidly focus on, rapidly develop code and functionality, but also focus on key sections of the application and not have to worry about interrupting the other ones. So what we used there was a lot of RabbitMQ message broker to pass messages between services. We also used caching logic where we would write information to a cache, and then later on we would pick that information up in a different application. So one of the things that also made this very easy to work in a microservices architecture is the use of Docker for containerization. So we've got a bunch of applications. We need to run these applications. What's the most flexible way to do it? Wrap them in a Docker image and spin up a container. This allows us to easily ship applications to our deployment server without having to install loads of dependencies on a server and try and manage that server and keep it running. So for instance, we needed Node.js running, we needed Golang running, we needed RabbitMQ. Let's just use Docker containers, shrink wrap the functionality and push it to our Kubernetes cluster. So we use Kubernetes to deploy our containers and to keep them running. So Kubernetes is a fantastic piece of software for managing the orchestration and deployment of containers. And again, we used our GitLab CI pipelines to automate the generation of the Docker containers for each of our applications and also deploy our containers using the GitLab CI functionality. So gonna have a quick look here. This is our Kubernetes manifest file repository. So there's a bunch of different files in here for each of our services. As you can see, we've got like Postgres database, we've got RabbitMQ, we got Redis, we've got our Twitter or our Telegram bot, we've got our dashboard application, bunch of different applications in here. And each of these would have its own kind of manifest file that describes what the container should do and what it should be able to connect to. And within here, then we've also added our GitLab CI file. And this allows us to essentially, so one of the great features with GitLab is you can integrate a Kubernetes cluster with your project. And by doing that, it allows you to execute Kubernetes manifest files directly against that cluster, which is very useful again for this project, as we didn't want to have to manually deploy things and tediously run Kubernetes commands unless we really had to. So one of the things that we did was we bound our Kubernetes cluster to our repository. We created a CI file, and then we added the Kubernetes executor, which allowed us to, the Kubernetes CI executor, which allowed us to run kubectl commands and apply our files from our CI deployment. And one of the great things about this is we can actually use a manual trigger. So, okay, for instance, I want to change one application, but I don't want to tear down the whole stack just because I changed one application. So what we can do is we can use the manual trigger, which then means as an administrator of the system, I can come in here and I can decide which one I want to deploy. So for instance, I've only changed the Telegram bot. Well, I only need to click the deploy button for that bot. I don't need to deploy the rest of the stack, which is very useful for moving quick and having predictable builds and predictable deployments. So GitLab was kind of essential in this project for making things a lot easier to work with and simplicity. So we used it for automating our builds, we used it for automating our infrastructure, we used it for automating our deployments to Kubernetes. Very, very useful tool, and great features in the free pack. So one of the other things we also used was Google Platform. So most of our application is deployed on Google Cloud Platform. And all of our data processing that we discussed in the previous slide is executed on Google Dataproc, which is a kind of a wrapped version of a bunch of open source data processing tools built on the Hadoop platform. Very useful, very easy to work with, and Google have done a great job of packaging that up and making it as simple as possible to use. So that's kind of the tech, that's the data. We've talked about the motivation. So how does it actually really work? So as we've discussed earlier, the whole application is kind of executed in a daily automated process. Well, initially it was a daily automated process. So for instance, the Johns Hopkins data is updated daily. Well, we don't want to be checking for that data every 5 minutes. So what we do is we run a nightly job, which basically, we use a Kubernetes job. Kubernetes offer a feature like a cron job, which means you can execute a container at a set predefined interval, and essentially Kubernetes will schedule that container to run. The application will do what it needs to do, and then that application will terminate and the job will finish until the next cron interval triggers. So what we did was we built a Golang application which allowed us to use the Google Dataproc API. And within that Google Dataproc API, we were able to trigger the automated creation of a Google Dataproc cluster. We would then push some Python files to the cluster that were our PySpark and our Apache Pig jobs. We would sync our data from the Johns Hopkins repository, push it into the Google Dataproc cluster, execute our jobs, and then once completed, we would update our database with the result files, and then we would terminate that cluster. The fantastic thing here is that this allowed us to predictably schedule the data processing tasks, and also we only use the cloud resources when required. So this is a good idea. The API is essentially very, very good. And so instead of running a Dataproc cluster for 23.5 hours of the day when it's not being used, we were able to run it for that half an hour when the data processing actually happened. So our Kubernetes cron job would kick in, the cluster would get created, the jobs would trigger, the data would get transformed, and roped to our database, and then the whole cluster would get torn down, and then the whole process would get scheduled again for the next day. So that's kind of how we processed and synced the data. But then, okay, so we've synced the data, we've added it to our database. Well, how does the front end update? So one of my kind of strong views on dashboard technology is that it should be real time where possible, and a user should not have to, excuse me, user should not have to interact with the system to get data refreshes. So for instance, with the dashboard we've built, we don't want to have to click a button to get the new news, or we don't have to click a button to get the new stats. We just want them to appear when they're ready. So we use the push model. So instead of the typical request response for the client side, we use a push model. So within our application, we built a front-end application, and what it uses is a technology called WebSockets, and we use a library called Socket.io. So there's a Node.js server in the background that runs the web server that renders the HTML, or that at least serves up the HTML file to the client. When the client application initializes, it creates a WebSocket connection using Socket.io back to the Node.js server. The Node.js server essentially says, hey, I am waiting for a connection. So actually, I have a good schematic here of what's going on. So we trigger the Kubernetes scheduler job to basically say, I need to get the latest data stats. The job executes, it reads from the database. It gets the latest country data and the statistics data for that particular day. That data is then pushed to a Redis cache. A notification is put onto a messaging queue, and then the backend Node.js application, which has a queue subscription to the front end, a socket subscription to the front end, detects that there's a new message coming in. So it says, oh, I've got a new message. What do you want me to do? Okay, I need to retrieve the latest information from the cache, and then I'll give it to the front end. So the front end is essentially waiting for connections, for updates, and then when the back end receives an update, use it by this automated schedule process, it pushes the notification to the front end, and the front end renders the data without actually having to initiate anything other than the initial create socket. So this is the kind of update mechanism. But what happens when a user first opens the web page? So what happens when the user first opens is the WebSocket connection is created to the backend. The backend has an event handler that says, when a new socket connects, I need to do something. So what does it do? It just retrieves the latest data from the cache, and then it renders it to the user. So every time a new user connects, they just get the latest cache data, which means we don't have to do any database reads. The cache is done in Redis, is very quick. And then in the background, we can basically automate the scheduling of the cache updates. So this process is completely detached from the user having to request data, which means we can serve that data up quicker. We can push it to people when new updates happen, and no one has to actually trigger any action to get that data. I probably skipped ahead, but this is the more complicated flow. This is the PySpark data syncing, John Hopkins data crunching process. It does look very elaborate, but in reality, it's very, very straightforward. So what happens? We schedule our cron job. We go into our Golang application, and it has a bunch of tasks that it needs to operate. So the first thing it does is it clones the John Hopkins repository into memory. It filters out the days that it doesn't care about. So it always wants to get the latest day. Once it finds the latest day, it does some mild data processing to produce a CSV file, and it pushes that to a Google storage bucket. Once it's pushed it to a storage bucket, it takes the PySpark and the Apache Pig job execution files that will be used in a later stage, and it also pushes those to a bucket. The reason it does this is because we can version one application, and the data processing files are versioned within that application, which is very, very useful because it reduces the amount of configuration for this application. You basically ship one binary. That binary has all the data processing code contained within it, and it knows how to trigger and execute itself. So after it's pushed the data processing files to a storage bucket in Google, it then goes to create the Google data proc cluster using the Google Golang SDK. So it triggers a creation of a cluster. Google goes and processes that, spins up a cluster for us based on the configuration parameters we set in the API. Once that is created, we then trigger our data processing pipeline. So the first thing we do is run PySpark. So we trigger, or sorry, the first thing we do is run Apache Pig. So we trigger a pig job process. And what this does is it looks at our CSV file that we have synced from Johns Hopkins. It loads that into Pig. It then loads the Pig job execution file that we put into the Google bucket, and it runs the Pig job. It processes the data, swaps out the nulls we talked about, sanitizes the data somewhat, and then it pushes the result CSV file into a Google bucket. After this executes, we then run PySpark on our results, on our Pig results. PySpark basically does several different things. It produces a couple of different data sets. It produces a list of unique countries and the totals for those countries. It does some extra analysis on the cases, like figures out who the active cases are from the existing data, figures out if there's any other processing that needs to happen in there. Again, it uses the PySpark file that we pushed to a Google data bucket in an earlier stage. Once that finishes, it creates two files. It creates the unique cases per country, and it creates the cases, the overall cases with some additional fields added to it. Once that PySpark job terminates, we then do some analysis to figure out if there's any of the PySpark data has any missing geolocation codes in it. So as we talked about earlier, some of the Google or some of the Johns Hopkins data has missing fields. So in the earlier records, there was no geolocation data in there. So we want to have a uniform data set. So what we do is we pick a subset of the case data that has no geocodes. We push that data to a bucket. Again, we trigger a PySpark process. That PySpark process gets its script file from the Google bucket from our earlier stage. It then runs a Google API geocoding call for every item in that list, goes to Google, does the geocoding, gets the results. When it finishes its job, it then pushes the geocode result CSV back to a Google bucket. At this point, we have finished our data processing. Now it's time to update our database for persistence. So what we do is we finish the geo processing. We come back into our save country data. So now at this point, we've got multiple output files. We've got the country data, we've got the case data, we've got the geocode data. So what we do is we trigger several different database updates where we write our country data to Postgres, we write our case data to Postgres, we write our geocoding data to Postgres. So we update the data that's missing in the database. At this point, we are nearly ready to finish our job. So remember, this all started from a Kubernetes scheduled job. So as you can see, we've created a bunch of different artifacts in the Google buckets. So now it's time to clean those up. So what we do is we trigger some data process, or we trigger some Google bucket deletion, again, using the Golang Google Cloud SDK. We delete the files that we've created. So next time we run, we will have a clean data set. And we also finally terminate our dataproc cluster. And once this is finished, we have done our full end-to-end data processing for the latest data set. We've updated our database, we've filled in missing fields, we've sanitized the data using this various different pipeline. And then we terminate the Kubernetes job. And then Kubernetes will reschedule this job for the next interval, which is the next evening. And that is how we do our data processing. And as discussed in the previous, I probably did these the wrong way around, but as discussed earlier, once that data is in the database, we now need to show it on the front end. So this is where we have the front end update process that we discussed earlier. And this again uses a detached, this runs in a more frequent interval than daily. So what we do here is we trigger the cron job, we read the latest data from the database, we push it to the cache, we push it to the front end. The fantastic thing about this process is we can run this very, very frequently, and only when something has changed, which we can detect here, do we push it to the front end. So the front end only receives the latest updates, where we can run this at a very frequent interval. Our news API data processing is in a very similar process to this as well. We run Kubernetes job, we read from the data API for the news, we push it to the database, we update the cache, we push the news to the front end. So that's kind of how we do all of our data processing, how we update the front end, where we get our data from, how it's all executed. And essentially, we have a bunch of microservices that all hook together. So basically, thanks for watching. Thanks for listening. This was a very fun assignment, very interesting. Lots of cool technology to play with, lots of interesting things. Hopefully, COVID-19 does pass soon and we can all get back to normality. Have fun playing with the dashboard. This is going to keep evolving as this case grows. I will be adding more functionality to this. I will be constantly tuning it. I will be making it a lot better. I'll be adding more stats, making the user interface a lot more granular, the ability to dive into countries and see exactly what is going on. There will be more charts. This is by no means a finished product. So yeah, watch this space. Thanks.